All right, hello everybody, and welcome to another edition of Space Class with Salsa Sommelier. That's me, I'm Salsa Sommelier. And so today we're going to be doing an intro to navigation. And so we're going to skip right into what we're going to be doing here. Let me just kind of write out what we're going to be doing here. Step one, we're going to draw a little picture. Hello. And in there we're going to define a few things. The next thing we're going to do is define what a covariance is. Look into the covariance and some of the statistics behind it. And then the last thing we're going to do is tie all together and talk about the actual extended Kalman filter and the actual formulation of that. And then finally, we're going to throw all this into a simulation to show how all this stuff works together. So the first thing we're going to do is draw a picture of what's happening here. So I'm going to make the screen smaller. Let's see. Take that out. Okay, so the problem we have here for navigation, orbit determination, is you've got a satellite or spacecraft. We're going to make it a little ball with some solar panels. He's flying through space, right? So let's put his trajectory in a blue line. That's where he's going. This is where he came from. This is where he is now. And so we're going to call this line f of x, comma, u. Don't worry what that means. This is just the function. This is where x is. This is a function that defines where your state x is as controlled by a control vector u. So you've got your satellite. He's flying through space as a function of f of x and u. And we want to track it and see where he is. So the most straightforward way to imagine that is with a ground station that does a coherent tracking, where it sends a signal up to the satellite receives it, and then sends it back. And we call this measurement y is a function of x. So y is the actual measurement, and the measurement can be something like range or range rate. It can be GPS. It can be angles. These are all valid. It can also be things such as cameras. Eventually cameras give you something like a range rate, or angles, but you can kind of have a layer of abstraction where you're using a camera. You can really use all kinds of stuff to create your measurements. There are also star trackers. I don't need to go on to that. What you need to know now is that we create measurements of our satellite. Our satellite flies through space as a function of where it is and what we're doing to it. And so what we have here is our spacecraft going through time, and we create an estimate of it. So we have a estimated state, and we'll call that x hat. And we call the estimated state is the expected value of x at a given time. So we'll say the expected value, the estimate of x at t is the expected value of x at t. And we're going to get into like how we set all that up, what that all means. Wow, you can't even see the greens on here, huh? All right, I'm going to avoid green. Let's go back to blue. So x hat is the expected value of x, which basically means we expect things to generally behave in terms of that we take a measurement of it, and the measurement of it generally tells us where it is in the measurement space. And so we need to translate what that measurement space is into the force model space, or your actual space. So what I wanted to draw right now here is that you usually have, or no, not usually, but always have an initial estimate. So we'll come in with an x naught. and that is our estimate at time t naught. And so maybe that's over here. So maybe this is your t naught, and you go through time, you pick up some measurements, and you're going out, and now you want to know where you are at this time when you stopped at the very end, where you stopped taking measurements. So you've collected measurements through some time. You want to create an estimate of where you are, where you're going, and then we also need to take that and propagate it forward in time per this function that we know. So that's the very high level what we're doing in order to do, I guess, deterministically. You take a measurement of something, it tells you where it is. That's how we do it. So unfortunately, we live in a stochastic environment. So the measurement we have, any measurement we have, has noise, and we'll call that eta. We also don't fully understand the dynamics, so we have this thing here called process noise, which is omega. We'll call that process noise. This eta is measurement noise. And finally, what I did not mention is a bias, and I'm just going to actually do a little magic now here and move this guy over. Actually, yeah, I'm going to move him over, get rid of the stupid arrow, and we're going to, so we have measurement noise and bias. So the bias is B, noise is eta. So we have our measurement, we have our state, we have our initial estimate of x hat at t naught, but we also have an uncertainty. So we want to capture the uncertainty of where we are, where we're going numerically, so that when we statistically combine our uncertainty, our knowledge of where we are, with our knowledge of how bad we know where we are, we're going to call that the covariance. And there is a specific definition of what the covariance is. It is a matrix. We always use terms like covariance ellipsoid. Covariance is typically we like to call it an ellipse that captures the kind of uncertainty. So somewhere, this is where I'm going to start drawing some ellipsoids, right? So we have our spacecraft here, and now it's just here. I'm not going to draw this. We're just going to say SC for spacecraft. So forget that. It's there, but we don't know exactly where it is. So we bound where we think it is by some area, and that area has some principal shapes about it. It's got it also has this angle to it. You'll notice that these are rotated by some angle. So what this all tells us is that this ellipsoid is defined by a major axis, a minor axis, and a correlation angle, so that you can rotate, from our XY plane here to this, to our nice little covariance here, which is kind of off at an angle. So these we have our axes and our correlations, and those give us both our uncertainties, otherwise known as sigmas, and our correlations, which kind of tell us how these guys change together. So let me get rid of some of these guys. So we have our spacecraft in his cloud of uncertainty, aka the covariance, and we're taking a measurement of it with our ground sight down here. That's a really bad line. Let me try that again. Right here, right? And so here's our little satellite dish, and he's taking a range measurement directly overhead. And so what you can imagine, just by looking at the geometry of this problem, I'm going to do a little more magic here because I'm not lining things up right. Okay, so we took a range measurement of our guy here, and because it's a range measurement of just from one direction, it has no, there's, it can give you a range. And so like we said earlier, it's a function of where it is plus some noise and a bias, but where it is only gives you a single number, range. And that is range from this single ground side. So that tells you it's only got resolution in one direction, that is along the range axis. So what happens as we process this data is that we get an update to the actual position. So we'll break this up with a little. So this is T0 minus and T0 plus. So this is right before we process the measurement and right afterwards. So we process that measurement and we find out, oh, we're not here, we're actually up here. So you can see I've kind of shifted it up a little bit. And because we took a measurement in this direction, we have a much higher confidence in its position along this direction. So, but because we have no resolution or visibility in, normal to the range direction, our new covariance is going to look something like this. Actually, let me make that even more pronounced. In fact, that's still not very good. It's still at an angle. Let's say we removed some of that. We removed some of that uncertainty. So now, and I'm going to do some more magic here. I'm going to pull these guys. And so now, after we've taken our measurement, oh dear. Now that we've taken our measurement, we've got an updated position and velocity. We've got an updated state, so we'll call this x hat naught plus. We've got a covariance, a new covariance. This is our covariance afterwards. And so we're tying all this together. And so the next thing we're going to look into is the actual math. So next page. And to make this a little more easy, I'm actually going to just go over to Wikipedia, and we're gonna go through these terms. So what I'm looking at right now is the extended Kalman filter page from Wikipedia, and I'm going down to the discrete time measurement, continuous time, discrete time measurement, extended Kalman filter. And so you may already recognize some of the things that we've seen. So what I'm going to do is grab this. Let's zoom in a little more. Let's grab this whole thing. These are all the equations we need. And we're going to copy it, and we're just going to drop it over here so that I can mark directly on them. So you'll notice already some things that we've already seen, such as f of x and u. We've already seen that. This is our satellite flying through space. This is our process noise. This captures what we don't know about the dynamics. And so this process noise is a function of time. It's normally distributed about 0, and it's a matrix whose diagonal is defined by, we call this the spectral density matrix. Spectral density. So now that is how we kind of capture both our force model through time and the uncertainty of that force model. We don't have perfect knowledge of gravity out there. They're using z. I used y. Z is a function of the state plus this looks like noise. They're not including bias. Sometimes there's bias. Not important right now. Again, it is normally distributed about 0 and has a measurement noise sigma right here. So when we say something like a measurement has a 1 sigma noise of 5 meters of range, so we'll call this, we're just going to call this measurement noise. So, and this is where x of k is x at time tk. So what did I say earlier? The x hat at time naught is the expected value of the state at the first time. And then this p is actually what is typically what we call the covariance. And you can see it's the expected error between the state and your estimated state, transposed and multiplied into a square matrix. So you get both along the diagonal of this matrix, you get the square sigma squares, and then this covariance matrix is semi-positive definite, which means, and symmetrical, which means, let's see, so I'm going to change colors here. We're going to have sigma squareds in the diagonal, and then we have correlation terms in the off diagonal, and these correlation terms, these two sides are mirror each other. So there's a correlation. Oops, ran off the screen. Okay, so we have two kind of sides of the Kalman filter. We have our predict, and then we have our update. So prediction is, if I go back a couple pages, prediction, let me blow this guy back up. Prediction is this time span. You can't see mine, so I'm gonna have to draw. You can't see my cursor. So prediction is any time where we don't have measurements and we're having to just take our estimate and push it through the force model over time and hope we end up where we expect to. That's why we take measurements to refine it, and that's the update stage. So let's go back to where we were just looking at. So we understand our force model, and so we push our estimated state through the force model from its initial initial guess, or if you're working in kind of a batch, in a filter, you're marching from time step to time step, taking in measurements, moving on to the next step, taking in measurements. So to just generalize that, we say TK minus 1. So the next prediction starts with the previous update, and same thing with the covariance. And so probably the most important thing to note, this is what one would call the punchline, the money shot. This equation right here is how you propagate your covariance forward in time. So once again, going back to, actually, I'm just going to go back here, but I'm going to redraw it over here. So we have our satellite going through time. Oop, that's really bad. I want to make like a nice pretty arc like that. So this is going through time, and so over here we have our initial covariance, and we're propagating it through time, and it moves over here, and you can kind of tell something's happened. It grew, right? And oh man, I'm not really good at this. Okay, so our covariance grew, so we'll call this P K minus 1, and this is P K. So we went from TK minus 1 to TK, and so we're moving both our X hat, which would be kind of our estimate, which typically is right in the center. Usually take your, you take the center of your covariance, that's where your estimate is, move it over time to TK. Now our covariance has changed shape, changed size, and that's all driven by this equation right here. So what is F and what is Q? Well, going back, we saw Q earlier. There's our spectral density matrix. Q is our spectral density matrix that feeds process noise into the propagation of our covariance. And F is right here. It is the Jacobian of our force modeling. So what you do here is you take partial derivative of your F with respect to all of your state parameters at a given estimate with a given control, and then that is what is fed into these capital F of T's. And so this gets you to what they call the X hat of K from K minus 1. So we are at time K from K minus 1, and this has not the reason we have this as seen by K minus 1, excuse me, keep pushing this button, is because we have not taken any data yet. So we haven't introduced any new information to the system. all we've done is taken our previous state and push it forward in time to the next time span. So once we are there, it's time to update. So from here, I'm just gonna recast that back over here. So now we're at TK. This is the next step. So we're at the update now, right? So we've got our big covariance. We've got our estimate lying in the center of that covariance. And so what we do is we calculate our Kalman gain, and this has a few parts to it. And so we see this R. This R is a guy we've seen before. This is our measurement noise. This is a matrix of measurement noise along the diagonal. And so the pH transposed divided by HPH transpose plus R gets you our Kalman gain. What is H? We just saw that, right? Or we didn't just see that, but maybe you're looking ahead, and H is the Jacobian of our measurement model with respect to our state parameters at about our estimate at the right time. So we create this Kalman gain, and I'm not going to derive this stuff. You're going to have to watch some other video to derive these actual equations. These are all matrices. So we've got our covariance that we've arrived at. This is this covariance. So I'm going to write out its full name. This is PK as seen by K minus 1. And so that's where we are here. P, K, K minus 1. Same thing here. This is our X hat of K as K minus 1. X hat. So now with our Kalman gain, we can actually update to our new state, X of K, as seen by the kth update. So we take our previous state and we add the Kalman gain, which is actually the rotation that links the measurement to the, what we call here is the measurement residual, which is the difference between where you are and where you're not. Maybe you've heard that kind of silly word game where somebody tries to describe navigation by determining where you are but where you're not. That's what this is. This is the residual. So you take the difference between your actual measurement. So going back to here, we have an actual measurement, and we also have a, right here, this H of X bar at TK. So H of X hat at time K is your measurement model applied to your estimated state. So this residual tells you the error in the measurement space between what you actually measured and what you expected to measure. And so taking that residual in the measurement space and rotating it by the Kalman gain, rotating it and scaling it by this Kalman gain, puts it into the state space and updates your state. And likewise, you update your new covariance, P of K as seen by the kth update, as I minus your Kalman gain, your measurement Jacobian, and your previous covariance. Hello, put you back there. So that's pretty much it. So we're taking, we process our range measurement. So I'm just going to put a little zigzag here. So this is us processing with our big F of T, with our big H of T. So we're now updating, we're taking in this, and we're creating our K at our kth time. And so we get X hat K, K, and our new covariance post update. So this new covariance, we're just going to make it smaller in every direction. So now we go back to where we were. We have our new, let me write P, K, K. So we've got our X, K, we have our state at time K due to the kth update. We have our covariance at time K due to the kth update. And now we go back to where we were. And now we're at TK, and we're going to TK plus 1. And so now we're filtering. This is how we filter. We go back and forth between propagating, predicting, and updating. We just go back and forth between predicting and updating through time. And so let's start a new page, and we'll just see how this all works together at a kind of a black box. So what we have so far, we have our force model, who is f of x, comma u. We haven't really talked much about u, but just we can ignore u for now. It's f of x, whose Jacobian, the del f del x, we just call capital F. We have our initial state, x hat naught. We have our spectral density, which is, like I said earlier, a matrix whose the process noise in the diagonal. And this process noise right here is a tuning parameter. So if you don't have good idea of your dynamical environment, or if you know that your modeling of the dynamical environment is quote unquote insufficient, you may want to crank up some process noise, which then kind of inflates your covariance over time to account for that uncertainty. What that means basically is if you are, without these kinds of assumptions, you can create a filter that's far too optimistic. Then it thinks it knows the state perfectly, but it is wrong. And so we call that filter divergence. So a few things, there's a lot of behaviors that are kind of peculiar when you're filtering. So let me just finish this thought. So we have our force model and we have our measurement model. And of course, we saw that earlier, y of x, it too has a Jacobian that we just call, what do we call it earlier? G, H, capital H. We also have one thing that we kind of breezed over was applying our measurement model to our estimated state, and then creating our residual from that, y of x hat k. So remember we said earlier, this is our residual, and this is what drives the update. However, so how big is that update? The size of that update is dependent on a few things. Going back to our equations, the size of our update is governed by the size of it is governed by HPH transpose plus R. You can see that this is in the denominator as noted by the -1 here. So if we have basically, if we have a lot of uncertainty in a particular direction and our measurement has high sensitivity in that direction, you can expect your covariance to shrink, so to speak, quite a bit in that direction. However, if your covariance is already small, so to speak, I'm starting to use kind of more abstracted terms. Hello. If your covariance is already small, then it will not accept big updates, meaning it will process your measurements. Let's go back to here. So for example, going back to our little issue where we have covariance, we're going to look at two cases. We're taking a range measurement of this guy, this case, and this case. So taking a range measurement from this direction of spacecraft 1 will create a larger value update due to the size of the covariance. So we're going to say K big. Now over here, the filter, by having less distance in this direction, in this measurement direction, the filter effectively has higher confidence in the direction of in the position of the state in that direction. So it will not accept big updates. So if it's wrong, meaning if your state is actually over here, but you have high confidence that you're up here, the filter will struggle being able to move its estimate to where it really needs to be because the covariance is too small. We call it in that case, it's overconfident. And a way to reduce overconfidence is turning up your process noise, or turning up, I failed to write it earlier, y of x equals, I'm sorry, y is some function of x plus bias plus noise. We can also crank this guy up. We can either have noises that we know from, our measurement. We've been told that a measurement gives you such and such accuracy. We can take that and run with it. We can also take that and massage it to a value that makes the whole filter work better. So we are at 30 minutes now. I'm going to go ahead and stop here. And, I'm going to take some questions, assuming there will be any. And we'll dig in a little deeper with how we actually set this guy up in simulation, with maybe some specific measurement models, specific orbital regimes. But this is, and let me go back to what we've done. We drew a bunch of pictures. I showed you what a covariance is by kind of drawing these ellipsoids, ellipses of uncertainty, ellipses of ignorance. We formulated the EKF. I did not derive it. I don't want to do that. I just showed you what these pieces are and how they work. And then finally, what I did not really get to is how this guy all works in simulation, because we don't always have real tracking data of a real satellite. You want to be able to do all this stuff in simulation pre-flight. So next time I'm going to get into how to do that. Cool. Thanks, everybody.